Today we're going to talk about one kind of tree. It's not apple tree or lemon tree, but it's the kind of dangerous tree that can make you jobless. Alright, count unit value subtrees. Let's get started. Okay, make sure the clock is running. Alright, so given a binary tree, count the number of unit value subtrees. A unit value subtree means all nodes of the subtree have the same value. For example, given binary tree, we have 4. Okay, so let's take a look at it. We have 5 and 5, or obviously the one node is a subtree, and another 5 here, so we have 3. Oh, so 1, 2, 3, and then we have this 5 and 5. Okay, well this part looks like it, but the problem is it says all nodes of the subtree have this. Also, all nodes. The point is all nodes. So you can't just separate this part out of the subtree. You can't just separate. You can't just separate this part out of the tree, because all nodes of the subtree. If you treat this parent node as the parent node of the subtree, then all nodes include 1 and 5. So include this part. Alright, so the 4 means the result. Means this one, and this one, and this one, and also 5 and 5. So that's the 4 results we have. So okay, so usually if we have a tree problem, we would approach it in 2 ways: a breadth first search and depth first search. I don't see how we could approach this with a breadth first search, because you can't really do a so you say 5, and then you're gonna add it to a queue with 1, and you have 5, and then you're gonna check 1 has that. No, so it's really, I think this is more of a depth first search problem, because if you were to eyeball this question, if you were to eyeball to solve this question with your eyeballs, you're gonna just, first of all, you're gonna look at you're gonna start from a node and then go all the way to the end. But I think since we are using, so I think we will be better off with the depth first search approach. And the problem is, how should we do this? So I think now a depth first search, so it's a breadth first search is a top-down approach, so from the top to the bottom, and depth first search is a bottom-up approach, which means so from bottom to the top. Now, so we can start from the bottom. So we have 5. Now 5, we're going to check its child nodes. So in this case, the child nodes of 5 are both null, so it's true. And for this one, same situation, so it's true too. And okay, so when we move up to 1, all right. So when we move up to 1, we're gonna check if the parent. First of all, we're gonna check if the child nodes are the same. So if they're not the same, well, if they're not the same, there is no point doing anything. Okay, so okay. Now let me write down the okay. So if left is not equal to right, then we can just now, you know what? Let's not do the double slashes. Let's do a whole comment section. Okay, so now what the heck? It's 3 in the morning. I'm really sleepy right now. Anyways, so if left is not equal to right, then what do? Then there's no point doing anything, right? We just say, if left is not equal to right, say if 1 is, so if it says 3, 5, and then we got 1. So there's no point doing anything. This whole tree does not meet the requirement. We don't need to count. We don't need to do anything. So If it's not, then we just move on, okay? But however, if they are equal, okay? If they are equal, then we need to check if the left is equal to the parent or not, all right? And because there is one circumstance that's, so for example, if 3, 5, and we have 5 here, right? Just like, okay, let's take a look at this part, all right? 1, 1, 5, and 5, okay. So we have, well, I mean, actually, yes, it's this part, no, yeah. 1, 5, 5, excuse me. So left and right are the same, but they're different from the parent node. So if left is equal to the parent node, well, obviously it's not. So if it's not equal to parent node, which means this doesn't meet our requirement either. So we can move on. Or, all right, left is not equal to parent, right? Okay. All right. So else if we have these two, then we move on again, okay? And else, now, if they're equal, all right? So if they're both equal, then yes, we can count plus plus. So I think that's basically it. That's basically the logic, and I think we can start coding. So I have 23 minutes. Okay. So first of all, we need a global variable to keep track of the counts. So I'm going to have private int. We're going to have a count, and it's going to be 0, and we'll have a helper function, say, we're going to pass the root to it, and we will return count. Okay, so how are we going to implement this helper function? So we're going to have helper function. We're gonna to determine if the left is equal to right. I mean, to determine if to simply keep track of the current status of the child nodes. It's either meet the requirement or does not meet the requirement. So this is like a Boolean situation going on here. So so I think we can do a Boolean array helper function here. So it's gonna helper, and we're gonna have a tree node. Okay, and we're gonna have a node. Okay. So now, first of all, if the node is equal to null, all right. So if it's a null, then of course, now this is true. Now, there's nothing to debate about this, so we will return true. Okay, so now if this is not null, then we will pass it on. We will pass the left node and the right node, I mean the left child and the right child, to the depth first search, and in order to get a result. In order to get a result of whether our child nodes meet the requirement or not. So so it's gonna be Boolean, all right, left, and we have a helper. We're going to pass the left node to it, and then we're going to have another, so this is the result coming from the right child, and we're going to have a node right, all right? Okay, so, excuse me for a second here. I still have the flu. I fucking hate this weather. All right, so now, okay, so if now according to our logic here, right? If the left is not, if left is not, well, you can't use exclamation mark and equal. You have to say if they're equal. So in this case, since this is move on, then we don't need to say move on. We can just use a opposite logic. Say if they are the same. Right? If they are the same, right? Then we're gonna have some operation here, and then we're gonna skip it, and then so say if this is so in this case this is not equal, so which is we don't need to do anything, just return false. Okay, all right. And so if they are the same, okay, so if okay, first of all we need to check now node left is not a null node. Okay, if it's not a null and node dot left, so if it's not a null node and is not equal to node, wait, hold up, sorry, it's node dot left dot value is not equal to no dot value. Okay, or now this is our second condition. All right, so if node is left node is not a it's not a empty null, and also because it's not empty, then we can access the value and check if it's not okay. Now it's not equal to parent node, or okay, node dot right is not equal to null, and node dot right value is not equal to node dot value. Okay, in these two cases, right, we're gonna have, okay, we're gonna move on. So we're gonna return false, okay, because it doesn't meet the requirement. Okay, now if these are the same, then okay, we can count. So we're gonna have a count. We're gonna have a count plus plus, and then after that, this is a satisfied tree, right? So up until this point, this tree, the parent node of this tree is the same as the left node or the right node. So this is a perfect subtree that meets the requirement. So we're gonna return. So we're gonna return true. Okay. So that the parent node above the subtree will have information about whether this is a good subtree or not. All right. So I guess we can run a few test cases. So let me see how much time I have left. Okay, 6. Okay, so now let's try it with 5 or okay, just the example they provided us. Okay, someone texting. Okay. All right, so say we have 5 1 1 and oh, it's pretty nice. They have they visualize this. So 5 1 5 5 5 5. Okay, so first of all, my throat is so dry right now. This is, I hate this season. Leaving just. All right. So we have left. So first we go all the way to the left, right? So we have 5. Okay, 5 has 2 null nodes, and it's gonna return true. And then we go to the right. So this is a post order traversal. So this is a post order traversal. We have 5 here, which is also true, and we go up to this point, and okay, left and right, they're equal. But unfortunately, left node is not equal to the right node. Left node is not equal to, sorry, left node is not equal to the parent node. So in this case, all right, it's gonna return false. All right. So now count is equal to 2 right now, and we go up to okay, so we left node come back, and then we have right node, and then right node we're gonna traverse it to 5. So 5 plus 1 we have 3, and 3 we go up, and it's 5. Okay, 5 is in this case. All right, left node is null, and left node is null, and then right node is a 5. So according to the logic here, 5 is also true. So this is false, this is true. Return to this parent node. Left is false. So if you take a look at this in the background, left is false, right is true, which is not right. So we're going to return false. So it's not increasing. All right, so looks good to me, and we'll see. What the heck is this? 30? Helper? What the heck? Helper. Finished. Okay. All right, let's hope for the best. Okay. Oh, accepted. Oh, perfect. Okay, so now, wow, good. Yeah, the point of this is to I think one thing you need to take note of, you need to pay attention to, is all nodes. All right. So don't think of it as 555 this side, okay? Because all nodes includes all the way, okay? And the other thing is depth first search. So well, there's nothing to say about depth first search. So depth first search is a bottom-up approach. So if you try to solve a question with depth first search, you would need to try to approach this question with a bottom-up approach. So think of it from the bottom. So we're gonna start from 5 and then work all the way up to the top. Okay, anyways, that's it for this episode, and happy coding. I'll see you next time. Bye bye.